This is question number 1 on the conservation of momentum practice packet. The question has a ball that is made out of putty. It's moving towards the right here, and it smashes into this other rigid ball, which is much bigger. It's twice as massive. So the first question is, what type of collision is this? We can see from this sketch right here that the two balls hit and they stick together. And that's kind of further prompted or indicated by the idea that the first ball is made out of putty. So the thing you need to recognize is that since these two hit and stick together, we would say that the collision is inelastic. That's the terminology that we'll use for this type of a collision. Part B says if mass m is 2 kilograms, find the final velocity of the combined balls after the collision. We'd start all of these problems with a very similar statement. This is our conservation of momentum statement, saying that the sum of the momentum in the system initially before this collision occurs is equal to the sum of the momentum in the system finally after it occurs. This statement right here implies that momentum is conserved. It's an important thing to kind of start with because you can get points for at least acknowledging that momentum is conserved for this type of a problem. The next thing that I would do in this case, I'm going to assign each ball a number. I'm going to call the ball made out of putty ball number 1, and the ball that is not moving initially ball number 2. So I can therefore say that the momentum of ball number 1 plus the momentum of ball number 2 before the collision is equal to the momentum of ball number 1 after the collision plus the momentum of ball number 2 after the collision. I can further separate each one of these momentum terms into their constituent parts. It's going to be m1 v1 plus m2 v2 is equal to m1 v1 prime. This prime mark denoted with the tag, the apostrophe here, indicates that it's after the collision, times m2 v2 prime. Right out of the gate, you might have done this earlier, but you should recognize that the velocity of the second ball before the collision is 0. That makes this whole momentum of ball number 2 equal to 0, and it basically drops out of the equation. So I'll start this second line by saying that the momentum of the first ball is now equal to, I've simply eliminated that second term. I need to recognize something important here about v1 prime and v2 prime that's unique to this type of an inelastic collision. We need to recognize that v1 prime is equal to v2 prime. And that's because they hit and stick together here. So therefore, since they're moving together after the collision, they have to have the same velocity. We'll use a different variable, v sub f, to describe that velocity. We shouldn't be using two separate variables, in this case v1 and v2 prime, to describe the same number. So I'm just going to substitute this final velocity, or v sub f, for each instance that I have v1 prime or v2 prime. So now the right-hand side of my equation looks something like this. And in the next step, what I'm going to do is I'm going to now factor out v sub f, and I get m1 plus m2 times v sub f is equal to m1 v1. And in this last step now, I'm going to divide both sides by m1 plus m2. So I get vf is equal to m1 times v1 over m1 plus m2. And this expression right here for VF is an important one. It'll occur an awful lot in these type of inelastic collision problems. And so basically following our work up until that point in the box is important. At this point now, it's time to substitute some numbers in. I could put in 2 and 4 in for M1 and M2 if I wanted to. We will see that we could do this actually separately. Since we know that this ball is twice as massive as this ball, I could actually simply put in for M1 this value of m. For v, I'll put in 12 meters per second. And in the denominator, I'm going to get m1 plus m2, which is basically 3m, because it's m plus 2m. So in the denominator, I get 3m. The m's cancel out, and I'm left with 12 meters per second over 3, which is 4 meters per second. And so the final answer to this problem, the speed of the balls after the collision is 4 meters per second.